Thanks for coming to my talk. Thanks to the organizers for having me. I'm really glad to be here. So my name is Jakub Kozłowski. I'll be talking about functional programming and concurrency. Before we begin, I just want to make a disclaimer. I'm not a concurrency expert, although I know some things about FP, so I'll be talking sort of as a person who tried to do concurrency in FP. And just one more disclaimer. If you don't need to, don't do concurrent stuff. It's really hard, and if you can, try to avoid it for as long as possible. I want to start slowly before we dive into the deep stuff. So let's talk about our world for a second. Just think about how many things are happening right now. How many of you here are listening, browsing your phones, talking to each other? People outside are working, driving, so much going on. Billions of people and God knows how many animals and all the forces of nature. It's all changing our world at the same time. So we could say it happens concurrently. And it's incredible. This must be a really good simulation. But even if we are not living in a simulation, we as developers, we need to be aware that so much is going on. We need to be aware that the world is concurrent. And because of that, our programs also need to become concurrent. Because, for example, if you have a web application, you probably want to support multiple users interacting with it. If you don't, I don't think you'll succeed. And or your program might have multiple sources of input, like maybe some events from the network, some database changes, or just users typing things on the keyboard, even if you have just one user. So there's usually some concurrency involved. Imagine a modern sound editor that doesn't allow you to change the track that you are listening to. It would be pretty frustrating. So concurrency is pretty much a necessity in modern applications. Well, on some level, it has to be there. So what's the big deal? What makes concurrency so hard that I warned you not to do it if you can? And there are talks about it. Even on this conference, we had like 4 talks about concurrency. What's so hard about it? And I think it's just concurrent state, because if you think about it, it's always state on some level that causes the concurrency problems that we have. And most applications will need to have state. On some level, there will be concurrent state. Even a calculator application in your phone will have some sort of concurrency. Although very limited, you can still press 2 buttons at the same time, and the application needs to handle that. So just to sum up, there's always some concurrency. And for applications that have more state than that, whose state can be shared across users from the whole world, it might be a database, a queue, some external service owned by somebody else, or maybe something as real as the position of the sun. And the majority of programs will need to adapt to allow users to interact with them in a concurrent fashion, because that involves touching the state. And the problems that I mentioned, there can be many ways of breaking your program with concurrency bugs. You can have deadlocks, race conditions, and because of these, you can have corrupted data, or your application might stop responding at all. And each of these problems can have real-world consequences. But we're not going to talk about these consequences too much today. We are mostly going to talk about concurrent state. And in particular, I'll mention the most commonly chosen solutions for managing concurrent state in Scala programs, as well as a purely functional alternative. But wait, we already have something. We have tools for working with state in functional programming. We had talks about the state monad today. And why don't we just use the state monad, right? Well, if you look at the definition of a state monad, this is pretty simplified, but in general, it looks like this. The state monad is, I think it was mentioned before, it's just a wrapper of a function that takes the input state and produces the output state along with some value, the effect of this state transition. But guess what? It doesn't work with concurrency. And the reason why is because this is a function. State underneath is just a pure function from one value to another couple of values. And there's nothing more sequential than that. In the words of Fabio Labella, there's literally nothing more sequential than passing a value from a function to another function. By the way, I really recommend watching this talk. It's great, as are the other talks by Fabio. You should watch them. So does this mean that we cannot have concurrent state and keep all the benefits of functional programming? Absolutely not. But before we answer the question why that's possible, let's forget about FP for a while and focus on concurrency for the moment. So is this line, does this line make sense? Of course, its side effects, or at least it probably does, unless it uses some extra syntax for immutable data. It probably mutates some stuff, but is that bad? It's not, unless this is in a concurrent piece of code. If you try to run this from 2 different threads, then all sorts of horrible things can happen. And let's look at a bigger example. We have a user shopping cart class. It has 2 public methods, getSize and put. And put is supposed to insert the item that the user was in their cart. It will append the item if it's not already there in the cart. And the cart is powered by a list. So imagine we run this piece of code on 2 threads at the same time. We try to insert the same exact item. And what can happen if we try to get the size of the cart afterwards? All bets are off. There's no way to know if it's going to be 1 or 2. And it gets, of course, even more complicated if you try to do it in 10 threads. So why does this happen? Where's the problem? The problem is in these 2 lines, because they are not atomic. The operation of putting an item into the cart here is not atomic, which means that concurrent actions, concurrent executions of this piece of code can have different effects than running them one after another. So if we try to run the same code, insert the same item at the same time, both conditions will be true. The cart doesn't contain the item yet, and the code can insert the item twice. So one solution that used to be pretty common in Java and Scala used a synchronized block or another sort of lock, and it works. It does the job in this context. It will make our put method thread safe and atomic, but it has some issues. The first one, probably one of the most important ones in modern software, is that it's blocking. So if we try to put 10 items, even if they are different items from different threads, only one of them can do it at the time, and the rest will be blocked because there is no other way they can be suspended without blocking. And it's really easy to break. If you have more than one lock, then it's really easy to run into issues such as deadlocks. And because of that, locks are non-compositional. They just don't compose very well with each other. And by compositional, I mean that if something is compositional, you can understand the whole piece, the whole picture, by understanding the little pieces it's made of and the rules of composing them. And locks are certainly not like that. Another solution, very common in the Scala ecosystem, is using the actor model. It doesn't matter if it's akka or anything else, really. The rules are basically the same. The most important part of the actor model is sending messages. So here, our public methods are gone. They are now just data types that correspond to the messages that we send to this actor. And because an actor can receive and process one message at a time, this will also be safe for concurrent access. if we only interact with the actor through sending messages. And it has some flaws. It has, of course, the actor model is good for some use cases, but I don't think it's the right choice for something as simple as encapsulating some state, because the actor model might seem simple. You just send a message to some actor, but in reality, I think it's quite an advanced construct. It's very powerful. An actor is basically a finite state machine powered by a queue, which can change its behavior at any point while processing its messages. It can do any sort of arbitrary side effects. It can send more messages, create more actors, talk to the database, or, as I mentioned, change its own behavior. And, well, that's just too much power for this use case. In fact, most of the reasons I've seen actors be used is for this sort of thing, just encapsulating some state without talking to any other actors, or synchronizing resource access, both of which can be solved much easier with other solutions. And there's also this push mindset that the actor model imposes on you. So you wanted to call a method and get a result. Well, now you don't call a method, you send a message and you have to hope and pray that you get a response back. And in some cases, you won't even get a response, like in this put. You'll never know when it's been completed. You need to explicitly send back a response. And because of that, if you ask an actor with something, you actually have to specify a timeout every time. So you can get a timeout on the simple get operation, even though it doesn't talk to any other actors or leave the JVM boundaries. And it's also complex in testing. As you've seen, you need to, on one of the previous talks, you need to set up some test probes, have an actor system in tests, and sometimes wait and ensure that you didn't get a message. Of course, you can abstract that away in the state monad, which makes a lot of sense, but still you need to somehow test all the machinery at some point. And because of that, because of the actors are not as easy to test as pure functions, they are often neglected in testing. And they should be especially well tested because of all the non-determinism and the complexity of the model. So how about another solution, atomic references? Atomic reference is a tool that came with the JDK at some point. It's been here for a few years. And what an atomic reference allows us to do is call update and get, or get an update, and pass a lambda, which will take the old state of the reference and return the new state. So here, if the card already contains the item that we want to insert, we just return the old card. And only one thread can run this update and get at the same time, and there is no blocking involved. Other threads will just keep retrying. So it's sort of like a small STM. But this still has some issues. This is my talk and I make the rules, so I have to find some issues. The first one is that it's side effecting, because you have unit without any sort of I/O around it, and well, you have get that returns get.size that returns the long size, but that's not a constant. It will change over time, and it only allows you to update the value synchronously. So what I mean by that is, once you have a card in the update and get lambda, the lambda passed to update and get, you cannot make any database calls or do anything like this that is asynchronous or requires more effects without blocking. So you just have to return the new state. And because there is nothing that makes this class different from classes that don't have any state, the shared state here is very implicit. The code that will create instances of user card will never know that there is some state inside, and it won't be as easy to track where the state is being propagated. So maybe we can improve on this idea and come up with something better that solves these issues. And I think we can. So there's something called ref in in ZO, in ClassEffect, and it's basically a purely functional interface for an atomic reference. It also provides you a method called update that will atomically change the value inside the reference. But well, there's a variant that allows you to also return some result of this state transition, very much like the state monad. So you update the reference in a very similar fashion as before, and everything is now encapsulated in I/O. All the changes, all the lookup in the ref, and also creating the reference is also encapsulated in I/O. And we'll talk about that in a second. But there's still one major flaw. Well, not very major. Okay, there's one flaw with this solution. It still only allows you to do synchronous updates. So you cannot put an arbitrary I/O in this update block. But it's actually a good thing for some reasons. So on the previous slide, it was a bad thing. Now it's a good thing. Yeah. So I want to focus your attention on this part, I/O of user card, and why creating the ref is an effect that needs to be encapsulated in I/O. And to explain that, we need to talk about referential transparency. So it's a very simple rule, really. It just says that if you have a program and you have an expression used how many times you want in that program, you can replace all the usages of that expression with its value. And the behavior, the value, the meaning of your program will not change with that replacement. So as an example, we have a very precise approximation of the number pi equal to 3, and we use it in a tuple. Let's pretend that the tuple is our program. And we replace all the usages of pi in this program with its bound value, with 3. And it's the same exact program. So pure expressions, algebraic expressions, keep referential transparency. Okay, but you'll say, the moment we start doing side effects is broken. There is no more referential transparency. And even if with future, it's the same thing. Because one program will do the action once, and the other program will do the action twice. So this is completely different behavior. But it's really easy to work around that if you wrap your side effects in an I/O monad and make them first-class effects. Because this program on the left side will behave in exactly the same way as the program on the right side. And this is why creating a ref needs to be in I/O. Let's imagine it's not in I/O, for example. Here, we just create a ref using the unsafe operator. Don't use it, but just for the purposes of this slide, we are using it. And let's look what happens if we replace all the usages of ref with its definition. At the end of our program, we run the program unsafely. You don't really have to do that because you can stick your I/O in I/O app. But let's pretend we have to do it. So we get 1 because we updated, we increased the value in the reference, and then we get it. So what happens if we inline this usage? Now we get 0 because we are no longer updating and getting the same reference. These are two separate references. There's no more sharing involved. And this is pretty much a bug in our program now. So because creating a ref is in I/O, we need to do something else to share it. And we do that just by passing arguments to functions. So here we flat map on the value that creates a ref and run a program with it. And then we actually have a ref as a parameter. And we can do whatever we want with it. We can even we can actually run these concurrently and run more updates concurrently. It'll work. And this is really cool. And you can actually see that it's the same program if we inline it. You can actually see that this makes sense that we still get 1 if you substitute the implementation of prog with where it's used. Well, in where it's used. So this is the exact same program. And all we did was just inline a function. And I cannot explain this better than Fabio can, so I just stole some of his slides. But one of the most important things about this is that you make the sharing of your state explicit, because the moment you flat map on your I/O that produces the ref, within that flat map, you are free to use your ref as many times as you want. But when you are done with this flat map and you haven't returned the ref, it's gone. Nobody else will ever see it and modify it or see the state. And the higher you flat map in the call graph, the more sharing you'll have. So now it's not just a dynamic behavior. The sharing is not determined by how the registry of your state will behave, how you it's just easier to reason about, because you can see exactly what depends on what by looking at the code. So it becomes purely syntactical. And you can also understand it if you inline your usages into where the stuff is being created. And that also brings you more control over your sharing and more isolation of your sharing of your state. And maybe it's not really that visible now, but if we go back for a second to the cart, now the ref is injected to the user cart class. So it becomes easy to mock it, sort of, because we can just create a ref, make some changes to prepare the state that we want to test with, and create a cart with it. So referential transparency might not seem like a big deal, but it's really useful. It gives you the opportunity to refactor without, oh, that's the next slide, to refactor without fear. You can inline and extract common pieces of code or pieces of code that you want to name without any fear that you will break something. So it's just easier on your mind and your heart. And referential transparency is compositional, it scales. So no matter how big your piece of code is, you can always reason about it if you understand the smaller pieces that make it the whole, and the rules of composition, which are not really that hard. And all the dependencies between your state and where it's used become way more explicit, and so do your effects. So now there's no more a situation when you have a function that returns a string, but actually makes a call to the database. So just to sum up, side effects are bugs, and effects are really cool. So I want to talk about some things in Cas effect. Cas effect was probably mentioned a few times on this conference already, but just to sum up, it's a library from the type level ecosystem, a library for Scala. It provides an IO monad, things like fiber, which is also explained, type classes for reasoning about effects that allow you to abstract away from IO, and some concurrency primitives, which we're going to talk about. In particular, there's ref, which we already mentioned, deferred, which is a purely functional promise that we are going to use on some of the next slides. Semaphore, which is a purely functional non-blocking semaphore, which allows you to limit the amount of concurrency in some pieces of your code. And actually, you can do much more with that. And mvar, which is completely beyond the scope of this talk. So here's a task that I made up, but I actually had to create something like this for my demos. Let's create a combinator for two IOs that follows these rules. If the left one completes first, that's great. We cancel the right one and just return the result. If the right one completes first, we just ignore it and keep the left one running. But if this whole program is canceled at any point, we want to cancel all the running computations, both the left and right if they are still doing something. And because I mentioned cancellation, we need to talk about it for a second. Why is it important? Like 2 years ago, nobody talked about cancellation. A future cannot be canceled, but an IO can. So if you run two IOs, two programs at the same time using parttupled or some other operator that does parallel work, if one of them fails, if one of them fails, this operator will cancel the other one. So this will allow you to reuse the resources that it was supposed to use. If we have a very expensive job after 5 seconds and we get an exception after 1 second, then why bother with the expensive job? We can just stop where we are. And this works. And this also scales with like lists. You can run 100 IOs, and if any of them fails, you just cancel all the rest. Even if they are still running in parallel, you can just cancel them. So if I want to implement this operator directly with some low-level stuff like raise pair, which is defined for I/O, we're gonna have a hard time. This is not trivial code, and I think it still might have some leaks in the case of cancellation. So it doesn't really look good, does it? There are at least 3 places where we can hit cancellation and leak some resources. So this is why I had to do this bracket, this uncancelable, and guarantee case. And you probably don't have no idea what these all things mean. So can we do this simpler? Can we do this without using some low-level stuff like raise pair? So I want to introduce Deferred really quick. It's a purely functional promise, as I mentioned. It allows you to just wait on the promise without any blocking, or complete it once, exactly once. And there's no way to fail a deferred. If you want to complete it with a failure, you just have to give it a try inside or something else. So using deferred, we can actually solve the task quite easily because we create a shared promise, we flat map on it, the same way as we did on a ref. And in that flat map, it's going to be shared. So all this operator, all this cancellation work is now gone because we are using some very high-level stuff like deferred, the left shark operator, and the left parallel shark operation, the race, and it all makes sense. I don't expect you to understand it right now. I'm just making a point. And we can actually use something more powerful, like the memorize function, which takes any sort of effectful f that has the right type class, and it memoizes it. And the really important part of this is that it returns an f of a. So your natural instinct might be, okay, just flatten it, and let's use it, right? But if you flatten, and you use this value more than once, guess what? You'll be running the whole action that many times. It won't be memoized at all. So the key to using this memoization is flat mapping once, and in that flat map, you can use the nested f as many times as you want, but the effect will only happen once. And that has to be like this because of referential transparency. And here's where referential transparency shines. If you have really complex concurrent code like this, or even more complex, I don't expect that you will understand any of it. Maybe after a few minutes, if you know all the operators, of course, you will understand it. So let's make it little bit more understandable by giving things names. So I did some refactoring. I moved this piece of code from the end to the very beginning, this cancel all tasks, and I gave everything names. And I can easily do that without fear that anything will happen in the wrong order, at the wrong time, or twice instead of once, and so on. So the whole behavior of the program is the same as before, but the code is now much easier to understand. And this is the power of referential transparency. And you can build your own concurrent algebras like ref and deferred. You can use these two, combine them together to build really powerful things like circuit breakers, caches, internal job queues, anything that's specific to your domain, like maybe you have an encapsulation of a bank account balance, or you have an online multiplayer game and you store the health of the player. So we can actually create abstractions using these two and more. And functional concurrency is cool. And if you want to learn it, you can try it home, take your time, read these pages, read the ZO documentation, I don't care, just learn it. Use IO in production, we do, and we are really happy with it. And don't get discouraged if you don't get anything the first time or after hours of trying. It really takes a lot of time to get comfortable with, to feel comfortable with, even if you just feel so and aren't really there. So just take your time and keep learning. And for the next steps, you can just follow these links, do some tutorials, exercises, challenges. I encourage you to learn more about FS2, which was mentioned yesterday. It's a really nice library for streaming, queues, topics, all sorts of concurrency stuff. And look at all the libraries built with CasEffect. CasEffect is a common core for many libraries, and you can use them with IO from CasEffect or even with ZO. There will be a bunch of links on the next slide. And if you have any questions, just ask on Gitter. Someone will help. So here are the links if you go to the sites. This is all I have. Thank you very much, and I hope you have and you enjoy the rest of the conference.